All right, on to another problem, a supply and demand problem. So in this case, the fictional situation is we have three warehouses with a set amount of supply, a supply constraint, if you will. Then you have a bunch of demand nodes here, stores, if you will. And then lastly, you have on top of that different cost functions in supplying these different stores. So the cost for warehouse 1 to supply store 1 is different than the cost for warehouse 2 to supply store 1. And so all that can be seen here in the static conditions and constraints side that I created. And so if we go one by one and look at the elements, the first constraint is each store needs this many resources to exist, if you will, whatever that function may be. Each warehouse has only this much. If you sum the demand and supply up, you'll see that the demand or the supply exceeds demand. So we shouldn't have an issue with supplying all the stores and having them run. On top of that, like I said before, each shipping lane has a different cost function, which you see in this table. So once again, store 1 to get stuff from warehouse 1 is going to cost $3.50. From store 2 or warehouse 2, it's going to be $6. And then from warehouse 3, it's going to be $2.50. So there's going to be some optimal pathing to get supplies from certain warehouses over the other that we're going to have to try to figure out here in this problem. So on the right side is the problem set up. And so what I have here is the solution already pre-baked in. So let me clear that. So right now, as a placeholder, I've said that, okay, warehouse 1 is going to supply 1 to each store. If we look at it horizontally first, this is the total of I guess, supply going out of each warehouse. So for warehouse 1, in total, it gave out 4 supply, which is much less than its limit, 5,000, so it should be fine. If you look at it vertically, this is just the summation of how much resources the store has. So in this case, store 1 only has 3, 1 each from each warehouse. That's less than what we need, so that's not going to work, all right? So this is the setup though, like functionally though, it works. That's all we're testing here to make sure the math works, that the constraints match up. So once again, let's check. Store 2, the constraint should be 4125. It is. All right, that's good. And then likewise for warehouse 2, the constraint for supply should be 6,000. It is. We should be good. And then the cost function is very simple. It's just a sum product of what how the warehouses supply the stores and the cost. So behind the scene, how the sum product works is it'll look at the sell value. So in this case, let's just look at this one. Warehouse 2 to store 2, it knows that it sent one thing over. So it will look at this array, it'll look at warehouse 2, store 2, and say, like, to ship it over, it's going to cost $5.50 per unit. I guess that's the other thing I didn't say. This is per unit, and then that's how it calculates. So it just multiplies all this by this for a total of 53, okay? And so onto the problem itself and what we're trying to optimize. What we're trying to optimize is to satisfy all these constraints. Primarily this one, really. Like if we have extra here, it doesn't matter as long as we don't exceed it. But satisfy this and try to get this number as low as possible. And so right now we're at 1111. So this is a really low number, but it doesn't satisfy this. So we know that it does not work. So with that said, let's get solver going. So let's go to data. Let's go to solver. Let's reset everything to start from scratch. So what's the objective? It's going to be this value. What are we trying to do? We're trying to minimize the costs. What are we changing? We're going to change all these values. And then what are the constraints? This is your bread and butter. So the constraints are this total from each store has to be equal to this demand constraint right here. Okay, so we're going to press OK. Next, the total that shipped out of these warehouses must be less than or equal to their supply constraint. Okay, and then I think that should be fine. One thing what we can do is we can also just to bound it. So depending on the solving method, it will check in a direction, but what might help like minimize the calculation time is putting a constraint on what values you can put here. So I'm going to just arbitrarily say that, like, okay, you can go with any number here to figure out what number, but let's just say like the other constraints should hold it to make this within the bounds. But what might cut out a lot of options that we don't need to check from the beginning is we can say something like, okay, well, I know that at any given point, you can't have 6,000 here, so I'm going to leave that as my upper constraint. Once again, this is like just some arbitrary value that has some logic to it. You can pick 3,000, 2,000. What I'm just doing is I'm just trying to like limit the number of combinations the solver is going to have to do to get to the number, all right? And so a little bit, so a little bit is an art. So you don't have to always agree with me. Sometimes it's trial and errors, but I'm just gonna shove that in there just to see what happens. Then lastly, you have to just choose a solving method. So you have 3 types. Simplex LP is not appropriate here because this is not a linear problem. So it leaves these 2. GRG nonlinear and evolutionary. If you haven't seen the other videos, basically they're just different methods. One is not necessarily better than the other per se. It just really depends on the situation. GRG is going to approach a minimum through calculus. The challenge is it might find only a local minimum. Evolutionary will go and will do a random walk to try to find the minimum. It will be more guaranteed to find the true minimum, but it might take too long. But these days with computers, we should be fine. So I'm going to first start with GRG nonlinear to see what we can get. So we do this, we go to options. The combinations probably are a little bit greater. So it's 4, 12, 4 times 3. So there's probably a lot of different combinations it's going to want to do. So I'm going to just do 15 seconds. We're going to press OK. And then we're going to solve and see what we can get. So this is the number that it got. We're going to press OK for now. And so I'm going to change this a little bit so it's easier to read. Oops. Okay, so one of the answers is this. So I'm going to do this. I'm going to just paste the value. Okay. I'm going to do GRG lin. Okay, that's one of the solutions. I'm going to use this as a reference point. And then what I'm going to do now is I'm going to reset everything. And let's just see if we can do this again. So go back to data, and let's just see what it gets. 3908, let's restore, let's try again. 3908 looks pretty promising. Let's try something else. Let's do 20 seconds here. Let's see if that helps. Solve. Still fine. I also didn't restore the original values. The original values were that, so let's try that again. Oops. Okay, solver, let's try 20 seconds. Let's try 39018. Okay, so that roughly looks like it's small. One way to further enhance this is you can let it run longer, but it looks like it's solving before the 20-second mark, so it seems like it's pretty set on that value. So what we're going to do is we're going to reset it, and then we're going to now test the other way, evolutionary. So we're going to do this, solve, and let's see what it goes. See where it goes. So you see on the bottom, it went through a few iterations, 1,000, and in this case, it can only find 61,000. So the reason why it does that, and on top of that, what you'll notice is that it doesn't quite satisfy the constraints, so we can't quite use this. And part of the reason is because evolutionary solver doesn't respect true equals, and so in a way, you can actually could have assumed that you probably shouldn't use it for this type of problem. And the reason why it only is returning 61 is because of the nature of how it solves things, because it's going through every single random probability, it just hasn't gone down to 39,000. So as an example, if I were to plug in this value here, this combination, it would have had a better chance to find it. But once again, because it goes in every random direction, it would still take time to find this. So one way to get closer to this value is you can ask it to run for much longer. You can ask it to run it for like, say, 30 seconds, which I'm not going to do. Or you can change these conditions. You can change how exact it is. You can change its mutation rate. But once again, I'm not going to do it for this video just because of timing. And that would be ways that you can get it closer to 39 quicker. But just to iterate, the reason why it's only landing on 61 is because it's running out of time before it can find a much lower number. And one way, like I said, is you can seed it with something that's close, and it should be closer. But if you start from 1, it's just not going to get there. So here's what I'm going to do. I'm going to do this. I'm going to have it solve it by nonlinear, and it's going to get 39. Oh, no, it only got 55, so that's the local minima. So here's what we're going to do. So here's the double whammy. So the reason why GRG nonlinear is not finding 39,000 again is because it only finds local minimum values. It kind of operates on a peak and valley type of situation using the math. And so what's happening here is when it started with the other value, it started looking for lower and lower numbers, and it found 55. And then it started hitting 55,000 over and over again. So then it just made the assumption that, okay, this is the best we can do, and quit. When in reality, 39 is the much lower number. And the reason why it got there was because by doing 111 across the board, that was a better starting place for the math. So once again, if you let both methods run for a little bit longer, it could have probably got there. But in this case, it's not because of the reasons I just stated. So if I run this again using this, I wonder if we can get a lower number. There you go. See, it found 39. So it's really just arbitrary on like where it starts and starts calculating before it can find that. And so likewise, because we start here, let's go back to GRG non or evolutionary and see from this seed if you can find something smaller than 39,000. So if you see here, it's solving 1,000 problems. It's found something that's 38,000. So the number it found was 38,000, which is lower than 39. So this is an example of how evolutionary is probably the better method, but well, no, this is a good example of how evolutionary found you the better answer for your problem. But once again, it also depends on the overall circumstance. So see here, it couldn't find the total constraints. So even though it found a cheaper way of supplying, it would still fail because it didn't find the exact constraint of like this has to equal. So in this case, really the answer is you have to use GRG nonlinear, solve it, and then if you see here its exact numbers, this would be the true answer. This would be the true answer of how you'd fulfill each store. There might be some different combo, but this is a good enough answer because it satisfies the constraints.